Euclidean Geometry, Similar Triangles, Part 2. In Part 1 we introduced the similar triangles. We showed how to go about proving two triangles similar, much the same as congruent triangles, and a bit of use. Now in Part 2 we're going to look at similar triangles in circle geometry, and the way we're going to do that is to look at two riders and prove triangles similar in order to establish various other facts. Here's our first example. We have a tangent to a circle. We have another line parallel to the tangent. We have all straight lines there, TSR and TVQ, and we have to prove that triangle TSV is similar to triangle RQV. Now, in order to prove them similar, what I do is I always look at those triangles and I say, well, which angles would probably have to be equal to one another? So in my thought process, there we are. I throw down the angles and I say, well, S1 probably equal to Q there, T probably equal to R, and V1 probably equal to V3. If not, then we can swap it around. But you see, the whole point is, I keep saying you mustn't wait for geometry to come to you. You must go forward to it and ask yourself questions. So, first question. Is S1 equal to Q? Well, have a look. S1, Q2. Yes. Have a look here. Exterior angle cyclic quad. Now, if we look at the next one, T equal to RT, R2, it's a bit obscure this. It's a bit, so we're going to have to use one of those cases where we say, well, what is T equal to, or what is R2 equal to? Let's start with T, because we have some nice parallel lines there. Notice there. And I'll say, what is T equal to? Well, having a look at the parallel lines, Q1. Alternate angles, parallel lines. Now we ask the question, is Q1 equal to R2? I'm trying to prove T equal to R2. I have T equal to Q1. So I'll say, is Q1 equal to R2? And if you know your theorems, you'll see it immediately. Q1 equals R2. Yes. Tangent chord, or alternate segment theorem, or angle in the alternate segment. So therefore, yes, we have T equal to R2. We'll have to put the little proof into our proof of similarity. And therefore, V1 equals V3. So tough choices to why? Obviously, angle sum triangle. So let's do the proof. First of all, write the triangles. S1 equals Q2. Exterior angle cyclic quad. T equals Q1. This is part of a little proof now, because we're trying to get T equal to R2, remember. T equals Q1, alternate angles, parallel lines. Q1 equals R2, tan chord, or alternate segment theorem, or angle in alternate segment. Therefore, T equals R2. It's established. Side in the one angle in the one triangle equals angle in the other triangle. Therefore, the third part can always use angle sum triangle. Trust the angle sum triangle. Therefore, similar. With a case for similarity, angle, angle, angle. I remind you again, order. T is equal to R, first, first. S is equal to Q, second, second. V1 equals V3, third, third. Keep it in the right order. Now we have to prove the product of the length of these two sides equals the product of the length of those two. So the first thing I'm going to do is I'm going to write it in proportion form like this as two equal ratios. You can pull either TV below or TQ below, and you can pull either TS or TR below. It really doesn't matter. So I've left first, first, and pulled the seconds below, like that. Because we're going to do the vertical test, and we can do the horizontal test to see what we pick up when we go through, what letters we pick up. So going through vertically, we're picking up TSQ, TVR. They're both triangles, green and the blue triangle. And in fact, we say, is it feasible for them to be similar? With a construction, we'd have to do a construction, but yes, have a look here. Common, angles in the same segment, an angle subtriangle. So yes. But I don't like having to put in a construction. I will if necessary, and you can see how thought processes can lead you to constructions. Often students have said to me, but how do I know to put a construction there? Well, this will tell you. This vertical test will tell you. Put in a line SQ, join them, because now you can prove similar. But I'm going to look horizontally. I'm going to look at horizontal, and I get TSV and TQR. And if you have a look at it, those are also similar. Common, exterior angle cyclic quad, or angle sum triangle. And I prefer that one because there is no construction. So let's prove that one. In those triangles, we have T common. We have S1 equaling Q2, exterior angle cyclic quad. The remaining angle V is equal to the remaining angle R1 and 2, and we can say either angle sum triangle or external angle cyclic quad. I would go for this because it costs me less in ink, in effort, and time. Therefore, triangle similar. Once again, T equals T, common, first. S second, Q second. Angle S equals angle Q. V third, R third, V equals angle R. You don't have to have them in an order. I could have put S first here, but then I must have the Q first. They must follow the same order. Now I need that out of it. So I'm going to say, well, TS, there's the TS. It must go over TQ. First, second. So therefore I'll have the TS or the TQ. I'd be left with TV. So I need TV first, third, and it would have to go over TR. So that's what I do. Similar triangles proven, that for the fuzzy marker. And this follows straight on from there. Wonderful. Our next proof. We have a pair of equal chords and we have a tangent. Now equal chords, remember, subtend equal angles. Therefore A1 and 2 would be equal if you remember your theorems. Don't mark in everything you can see equal in a diagram because it could confuse you. I really don't suggest that. The thought processes I give you lead you to find things equal. And that's better when you say, are they equal? But there are two things I always recommend you mark in. And the one is, because these chords are equal, I would suggest you actually mark A1 and A2 equal to remind you later. And if you have a right angle due to I would mark those. Now, we have to prove C1 equal to A1. So, my thought process, well, what is C1 equal to? And knowing your theorems, you'll see it straight away. C1 equals A1 by tan chord. Alternate segment theorem, angle and alternate segment. Now the question is A2 equal to A1? Because then that would make A2 and C1 equal. And there's our big hint. They're both opposite equal chords. So yes, angles subtended by equal chords, or angles in equal segments. And therefore we can prove C1 equal A2. So the proof. And we're going to do exactly what we looked at. We looked at in the thought process. C1 equals A1, tan chord. A1 equals A2, angles in equal segments. And therefore C1 equals A2. Now we're proving these two triangles similar. So same as in the first one, I suggest you list the angles. C1 is likely to be equal to A2. Well, we've proven it. B1 and D, and then S and C. So C1 equal to A2. Yes, we've proven it. B1 equal to D. Well, if you know your theorems, you'll see external angle, exterior angle cyclic quad. Yes. And therefore the final pair of angles have to be equal, angle sum triangle. So let's do the proof in triangles. 1. C1 equals A2, proven. B1 equals D, exterior angle cyclic quad. C3, S equals C3, angle sum triangle. Therefore, triangle similar. I'm going to sound like a nag, but remind you again, correct order. B first, well, it was equal to D, therefore D first there. C second, therefore A second there. S third, therefore C third there, and case for congruence. Now this next bit here, and it worries me straight away, whenever I see something like BC squared, I say, do we have similar triangles sharing a side, so that BC can appear twice, once from the one similar triangle and once from the other? And there's nothing, so that does worry me a little bit. So we have BC times BC equals DA times BS. Let's do our vertical, horizontal tests, and we bomb, because we get an ABCD that way and ABCD that way. Now, you might remember from the past, if you've watched my earlier videos, if you get a quadrilateral and a straight line, so if you had BSC, which was a straight line, then you think, could it be proportional intercept theorem? Because proportional intercept theorem with vertical, horizontal will often give you straight lines and quadrilaterals. But no, it's not the case. So then I look and I say, well, I'm now bombing out, but then remember my problem was I saw this BC squared. So I say, well, hang on, BC is equal to CD. What if I took that BC and substituted CD, or that one, or both? I don't like both again because they're not two triangles sharing CD. But maybe I should put a CD instead of BC, because that's definitely not the case. So let's do that. There we are. CD pushes BC out the way. There we are. And we have CD over DA instead. We're trying to prove that, remember. This is our thought process. Now when we do a vertical test, we get triangle CDA and triangle BSC, which are feasible, and guess what? That's exactly what we've just proved. There. So we can prove it. We prove those two triangles. We go from that proof of the triangle similar to there. I want BC squared, or BC times DC, so I choose a BC from this first one, BC, so it has to go over DA. Now I want the DC below DC from the second triangle, first third, so I need a first third above like that. That gives us that product equals product, and of course now we can slot in that thing that says, hang on, DC and BC are equal. It's given. Therefore we can now put the BC instead of the DC. And we have BC squared equals DA times BS.